In the last section, we looked at what temperature is and how it relates to heat transfer and molecular kinetic energy. In this module, we'll cover the following somewhat more practical topics: temperature scales used in atmospheric science and the observed basic temperature structure of the atmosphere. So the temperature scales in meteorology, the most commonly used, preferred by meteorologists around the world, is the Celsius scale. For the general public in the United States, though, the Fahrenheit scale is more widely understood. So when meteorologists talk to the general public, they will fall back on Fahrenheit because that's what people are used to dealing with in the US. But I'll make the point that the United States is the only large country in the world to use it, and there's only two very small countries, relatively speaking, that also still use the Fahrenheit scale, and that's the Cayman Islands and Liberia. But for everyone else, it's Celsius. Now, when it comes to doing physical calculations relating to physics or chemistry, those generally require absolute temperature. And that's, again, because that is the measure of the degree of molecular motion going on, which is the energy of the molecules that can participate in chemical reactions and diffusion and a variety of other things. So if you're going to do physical calculations, then we have to start thinking in terms of absolute temperature rather than Celsius, which is a convenient scale for describing in relative terms where we are, but not in absolute terms how energetic the molecules are in water or air or what have you. So in meteorology, we use the Kelvin scale for absolute temperature, which is just a shifted version of the Celsius scale. By shifted, I mean the size of the degrees are the same. So a 1 degree change in Kelvin is the same as a 1 degree change in Celsius. The only thing is we've shifted it so that rather than the 0 point being at the freezing point of water, as it is for Celsius, the 0 point is now at absolute zero. Now, just for completeness, I'll mention that engineers in the US using the imperial system often use the Rankine scale for absolute temperature, which is a shifted version of the Fahrenheit scale, meaning the degrees have the same size as Fahrenheit degrees. That is, a change in 1 degree Fahrenheit is the same as a change in temperature of 1 degree Rankine. But again, it's been shifted so that 0 occurs at absolute zero. So just briefly, these are the kind of the key relationships between those scales, not including the Rankine scale. Kelvin starts at absolute zero, at 0 degrees, and the freezing point of water is 273.15 Kelvin, and it's 373.15 Kelvin for the boiling point of water at standard pressure. Well, Celsius is defined in terms of the freezing point of water and the boiling point of water, so it's 0 degrees at freezing, 100 degrees at boiling, and then you get to minus 273.15 to get to absolute zero. So again, you're seeing that all we've done here is shift the 0 point from the freezing point of water to absolute zero to get from Celsius to Kelvin, while keeping the 100-degree interval between freezing and boiling the same. Fahrenheit uses smaller degrees, and so we have 32 being the freezing point of water, 212 degrees being the boiling point of water. That's a 180-degree difference between the 2 points, and we have to get to minus 459.7 Fahrenheit to get to absolute zero. So just to reiterate, there's 100 degrees between freezing and boiling for both the Kelvin and Celsius scales, but for Fahrenheit, there are 180. That implies that for a 5-degree temperature change in Kelvin or Celsius, there's a 9-degree change in Fahrenheit. In the case of getting from Celsius to Kelvin, it's very simple. Simply add 273.15. That means the freezing point of water is shifted from 0 Celsius to 273.15 Kelvin, and absolute zero is then 0 on the Kelvin scale. If you want to go the other way, you simply have to subtract the 273.15. If you want to convert from Celsius to Fahrenheit, then you have to first multiply by 9/5, 9 divided by 5, to take into account the fact that Fahrenheit degrees are 5/9 as large as Celsius degrees. And then you have to shift to get to 32 for the freezing point of water. So you're multiplying by 9/5, and then you're adding 32 to get Celsius to Fahrenheit. Whereas if you're going the other way, you have to first subtract the 32 to get the freezing point of water to 0. And then you have to multiply by 5/9 to compensate for the different size of the degrees. It's really straightforward, pretty much easy to remember if once you've done it a bit. But oftentimes you don't need to do any calculations per se. If you have pairs of equivalent temperatures more or less memorized, or at least some of them memorized, then you can often translate from one to the other in your head without a great deal of trouble. So here's a set of values in Celsius and the corresponding values in Fahrenheit. And what you'll notice if you look at each column is that for every 5-degree change Celsius, you're getting a 9-degree change Fahrenheit. So 40 to 35 in Celsius is the same as 104 to 95 in Fahrenheit, and so on. And that's true the whole ways. And of course, the reference point here is that 0 degrees Celsius is 32 degrees Fahrenheit, and you can work your way in either direction from that starting point to get to all of the pairs in this table. So I find it useful to memorize some of these reference pairs, not necessarily all of them, but the ones that are maybe close to the temperature range that you're used to working with, or that you're likely to be working with. And specifically, that's the key one right there. 32 degrees Fahrenheit is 0 degrees Celsius. If you can remember that, which is easy, you could always get to the other pairs just by kind of rattling through changes by 5 and changes by 9 in your head if you need to. But might as well memorize a few key milestones or benchmarks on this table. 10 and 50 is very easy to remember. 20 and 68, that's basically room temperature. So if I say that we're at room temperature, you can think, well, that's roughly 68 to 70 degrees Fahrenheit, or maybe about 20 degrees Celsius. There's 30 and 86. It's 10 degrees up in Celsius. It's 18 degrees up in Fahrenheit. And, on a nice summer day, we're usually somewhere around 30 degrees Celsius. And then finally, 40 degrees. It's a pretty hot day when it's 40 degrees Celsius, and that corresponds to 104 degrees Fahrenheit. If you have even just these pairs of numbers in your head, or even some of those, you can usually do pretty well from there to estimate the Celsius temperature from Fahrenheit and the other way around. And of course, you can get to all the other reference pairs just using steps of 5 and 9 degrees. And then finally, you can interpolate when necessary, and you don't need to necessarily interpolate very accurately to get something useful. So for example, let's say that somebody says the temperature is 17 degrees Celsius, and you're thinking, well, I don't know what that is in Fahrenheit, so what is that? First, think about the pairs on the scale that are close to that, and the easy ones, or at least I consider these to be common pairs to think of. 20 degrees Celsius is 68 Fahrenheit, 15 degrees Celsius is 59 degrees Fahrenheit, 17 is midway between 15 and 20 degrees Celsius, and so in Fahrenheit it should be roughly midway between 50 and 59, and just by mental estimation you should be able to say, well, okay, the temperature is not too far from 63 degrees Fahrenheit. That's often accurate enough for just getting a general sense of where you are on the scale. If you need something more accurate, then there's always your calculator. It's not a hard calculation to do. So temperature is super important. It's central to how we divide the atmosphere into spheres. You might have heard the term troposphere and stratosphere. Maybe a little less likely, you might have heard of the mesosphere and the thermosphere. These are all definitions of layers in the atmosphere, starting at the surface and working our way up, that are defined by the temperature profile and what it's doing as you move vertically through the atmosphere. Also, temperature is central to understanding both horizontal motions, in other words, wind and circulations, and vertical motions, which is often what we call convection, related to convective weather like thunder showers and so on. So the temperature structure is super important for just getting to the basics of how the atmosphere behaves as a fluid and how to classify the different major layers of the atmosphere. And then finally, it plays a crucial role in cloud and precipitation formation, atmospheric chemistry, and countless other physical processes because of its relationship to condensation and evaporation of moisture, the rate of chemical reactions, and so on. So temperature, as well as humidity and wind, are conventionally obtained using something called a radiosonde. A radiosonde is a small instrument package which attaches to a helium-filled balloon, and as that balloon rises and carries the package with it, it broadcasts data back to a ground station that captures these variables as a function of pressure, which in turn tells you how high you are above the surface. Since the 1970s, satellites have assumed far greater importance around the world for measuring temperature and humidity and other variables because you can obtain measurements of temperature and humidity in places where you don't have people on the ground launching balloons. But radiosondes are still the primary standard to use to say, for example, compare with satellite measurements and determine how well your satellite estimates are actually doing. Here's a fairly typical temperature profile obtained by a radiosonde at a Midwestern station, in this case Dodge City, Kansas. This is in 2004, September 8th at 12Z, or 12 Zulu, or 12 GMT. If you want to call it any one of those, they're all the same. It translates to about 7 a.m. Central Daylight Time in Dodge City, Kansas. And this depiction illustrates some of the common features you'll see in a temperature profile from radiosonde observations. They're not all the same. They all vary, but they have some common features that you will see over and over again that are worth spending a little time talking about. So the first thing we notice is that the temperature starts relatively warm, down around 13, 14 degrees Celsius. If you look at the very bottom part of the curve, and of course the x-axis here is temperature, and the vertical axis is pressure, decreasing as you go upward, so it's actually proportional to height above the ground. And we're looking at the troposphere initially, which is where we live. We live in the troposphere, which is the lowest layer of the atmosphere. And within that layer, you'll see that the temperature generally decreases with height from the surface. So we're starting down near 15 or 20 degrees, well, not quite 20 degrees Celsius near the surface, and that temperature is decreasing fairly steadily as we go upward until we get to about 120 hectopascals, at which point it stops decreasing and begins to increase again. And that point where it stops decreasing is called the tropopause. That tropopause is the boundary between the troposphere and the stratosphere. So the stratosphere is the second layer up from the surface. And in this case, it's starting at about not quite 16 kilometers or about 10 miles above the surface. And the temperature in this case at the tropopause is quite cold. Just by eye looking at this depiction, it looks like it's around minus 70 degrees Celsius, which is quite chilly. But then it begins to increase, and by the time it gets to the top of this graph, it's up to minus 45 degrees Celsius or so. Now, before we continue, let's introduce some key definitions that we'll be using quite a bit through the semester. The first definition is the lapse rate. The lapse rate is the rate of decrease of temperature with height within a layer. And by rate, we mean a change in degrees per unit altitude. Okay, so it's really like a derivative. It's the rate of change of temperature with height. And we express that in degrees per unit altitude, most commonly in degrees per kilometer in this class. And second in terms of key definitions, an inversion is a layer in which the temperature increases with altitude. That is, the lapse rate is negative. And we've defined the lapse rate to be negative for that case because an inversion is really more of an exception than a rule. Usually the temperature decreases with height, and when we talk about the lapse rate, we just talk about the rate of decrease with height, but occasionally it increases with height. And so for that layer where the temperature is increasing with height, we're talking about a negative lapse rate or an inversion. Now, looking at this depiction right here, we can see this dashed line that's going diagonally along the curve for the troposphere, and that dashed line corresponds to exactly 6.5 degrees per kilometer. And we chose that specific slope because we'll see shortly that that is the defined standard lapse rate in what we call the standard atmosphere. Here we're simply comparing that standard lapse rate with what we observe to be the general decrease of temperature with height, and you'll see that they're not quite the same. It looks to me like that general lapse rate through the troposphere in this sounding is slightly less than 6.5 degrees per per kilometer, but it's not too far off either. But the other thing we'll notice is that there's inversions. They're not very deep inversions, mostly. That's an inversion where the temperature briefly increases with height. And we see another one right at the surface and a couple more small ones in the upper troposphere. And then finally, once we get past the tropopause, almost that entire depth of the sounding above the tropopause is an inversion, with a couple of small exceptions that I won't bother singling out. So back to the idea of a standard atmosphere. The detailed temperature structure of the real atmosphere varies widely from time to time and place to place. However, certain general features are common to many atmospheric soundings. And we already talked about the general decrease in temperature with height in the troposphere, and then the fact that that decrease stops when you reach the tropopause, and you may not get any more decrease. In fact, you'll get either no decrease or you'll get an increase. In meteorology, aeronautics, and some other fields, you don't often have access to a recent balloon sounding to tell you what the actual structure is. And in fact, if you're designing an airplane and you want to know something about its performance, it doesn't make sense to talk about a specific sounding on a specific day, because that may or may not be representative of the general conditions that you expect to experience flying that airplane. So what you need to do in many cases is make reasonable assumptions about what the temperature, pressure, and air density is likely to be at a particular altitude above sea level, keeping in mind that it's not going to be the actual temperature, pressure, and density on a given day, but rather something not too different than the standard values. So that has led to the definition of various standard atmospheres. And the one that I'm going to refer to here is known as the International Standard Atmosphere. It's an idealization that is most appropriate to a mid-latitude location during the spring or fall. Now I say mid-latitude because polar atmospheric temperature profiles are generally quite a bit cooler, or colder even, bitterly cold possibly. Tropical soundings tend to be somewhat warmer and to have higher tropopause. Also, even in the middle latitudes, it can be hotter than the standard atmosphere in summer and colder than the standard atmosphere in winter, so I'm going to say that probably it's more appropriate to spring or fall. So the point is simply that if you got to pick a standard atmosphere to work with for the purpose of looking at design factors related to aircraft or other things, might as well pick something kind of middle of the road. Not too hot, not too cold, neither summer nor winter, neither the equator nor the North Pole, but something in the middle, and that's what the standard atmosphere is designed to represent. It's important to keep in mind that the standard atmosphere does not prescribe humidity, which is another important variable, and part of the reason for that is because humidity is so wildly variable that you simply don't know what it's going to be on a given day, and it can be anywhere from near zero to close to 100%. So you're kind of left to your own devices when thinking about the effects of humidity. So let's come back to what is the standard atmosphere? What is the International Standard Atmosphere in terms of its defined properties? The first property that is set is the sea level pressure. The pressure is defined to be 1013.25 hectopascals at sea level. The surface temperature, that is the temperature of the air at the surface, is set to be 15 degrees Celsius or 288.15 Kelvin. And then finally, the lapse rate is set to be 6.5 degrees per kilometer, and that's 6.5 degrees Kelvin or 6.5 degrees Celsius, it doesn't matter, but 6.5 degrees per kilometer up to the tropopause, which is in turn specified to be at an 11 kilometer altitude. Above the tropopause, the stratosphere begins, and in the standard atmosphere, it's first isothermal, meaning that the lapse rate is 0, it doesn't change temperature at all, and then at some point it begins increasing until the stratopause is reached. I'm not going to give the details of that part here because they're not really relevant to this class, but those standard lapse rates and heights are given for not only the stratosphere, but also for the mesosphere and thermosphere. So anyway, from the definitions that are given, it's possible to actually compute not only the complete profile of temperature, but also the complete profile of pressure and air density in the standard atmosphere. And those are the things you generally need to know if you're talking about things like airplane performance or anything that depends on air density and pressure. For example, if you're climbing Mount Everest, the standard atmosphere will at least give you a pretty good idea of what you can expect in terms of air density or air pressure, which are going to have a very important influence on your need for, say, supplemental oxygen. Here's what that looks like graphically. Again, it's a standard atmosphere. It's very close to something called the ICAO standard atmosphere. The differences are not important for this course, but you'll sometimes see reference to the ICAO standard atmosphere, which is essentially the same thing. This is a very big view going from the surface all the way up to 100 kilometers if you look at the left axis. And we see the troposphere going from 0 to 11 kilometers, and then the temperature stops decreasing with height for a time until you get to about 20 kilometers, and then it increases a bit, and then it increases more, and at that point it stops increasing, and we reach what's called the stratopause. That's the top of the stratosphere. And then it begins to decrease again, and through that period, or that range where the temperature is decreasing with height again, we're in the mesosphere. And the mesosphere is prescribed here to continue in the standard atmosphere until about 79 kilometers, at which point the temperature begins to increase again, and finally we have the thermosphere. Now it's not shown on here, but the thermosphere has a temperature that increases quite a lot. It's called a thermosphere because eventually it may get up to hundreds of degrees, maybe even up to 2,000 degrees Kelvin if we have an active sun. And so that's quite a bit different than anything we see anywhere lower in the atmosphere. Now, just to put things in a context here, we can look at how this standard atmosphere relates to heights that we might be familiar with. First, there's the typical height that a jet airliner flies at, which is around 10 to 11, maybe 12 kilometers. If you are interested in the latest and greatest military spy planes, actually I'm not sure it's latest and greatest because the SR-71 has been decommissioned to my knowledge, but I believe it holds the record for the highest flight, level flight for a jet aircraft, and that was somewhere up around 24 kilometer altitude, so well up into the stratosphere. If we release a radiosonde balloon used by the Weather Service to measure temperature profiles, those will commonly go up to 30, 35 kilometers if they don't break too early. And we can look at the pressure scale on the right and see that we're talking about single-digit pressures in hectopascals. The highest altitude balloon record of any kind, to my knowledge, is 53 kilometers. And so by that point, we're getting to a pressure of less than 1 hectopascal, or less than 1/1000th of sea level pressure. Now the pressure, if you'll remember from an earlier lecture, is a measure of the weight of the atmosphere above that level. So if the pressure near the surface is around 1,000 hectopascals, then a pressure of 1 a pressure of 100 hectopascals is 10% of the sea level value, which means that 90% of the atmosphere's mass is below 100 hectopascals. If we get up to 10 hectopascals, 99% of the mass of the atmosphere is now below that level, and only 1% is above that level. And we can go on. By the time we get to the stratopause, we're typically looking at 99.9% of the mass of the atmosphere being below that level and only 0.1% being above it. So you can see the air is getting very, very thin. So even though there's a lot of distance still to go, the mass of the atmosphere is mostly below these levels. And so on. To 0.1, we got all but 0.01% of the atmosphere below that level. And we can continue on, and eventually we get to there's virtually no air left. It's all below that level. And 100 kilometers is what I like to think of as the point where we can really be talking about outer space. This is partly because of what I talked about earlier. This is where air stops behaving like a fluid and starts to behave like a lot of individual molecules flying around on ballistic trajectories that don't really interact with each other. It's not really behaving like a fluid anymore. There are other definitions of space used in other contexts, but for me, 100 kilometers is it in terms of the transition from the so-called homosphere to the heterosphere, because of the fact that we no longer have a mixed fluid. We have separate little molecules flying around. Now, the question you might have at this point, looking at this temperature profile, is why does it have the shape that it does? We've got a decrease in temperature in the troposphere, we've got an increase in the stratosphere, we've got a decrease again in the mesosphere, and then it increases quite a bit, starting in the thermosphere, and ultimately up to several hundred to maybe a couple thousand degrees Kelvin, if you go far enough beyond this graph. Why does it have that structure? A clue may be found in the fact that what we think of as the ozone layer, which is the zone in the atmosphere where there's a higher concentration of molecular ozone, that's located basically starting in the lower troposphere and then continuing until we get up into the mesosphere. And you'll notice that ozone layer corresponds with the range of heights where the temperature is increasing significantly with height. Why is that? The fact is, if you think back to what the ozone layer is famous for, and that is protecting us from ultraviolet radiation, the reason for that is that it absorbs the solar radiation. It absorbs the ultraviolet radiation. And if the ultraviolet radiation is being absorbed, it heats the gas that's absorbing it. So the ozone layer is basically absorbing ultraviolet radiation and is being heated by it, and it's being heated most strongly near the top of the ozone layer, and that's what gives us the big bump in temperature that separates the stratosphere from the mesosphere. If we go to the Martian atmosphere, and we've now actually taken temperature profiles from the Martian atmosphere using probes, we see a structure that looks somewhat similar to Earth in that near the surface the temperature decreases with height, but it continues to decrease, and then it reaches a minimum around, in this case, around 130 degrees Kelvin, which is quite cold, and then it starts to increase, and that increase is now the thermosphere. So there's no stratosphere. There's only a troposphere and kind of a mesosphere, which is sort of an in-between thing, and then we have a thermosphere, but no stratosphere. And the reason, of course, is that there is no ozone in the Martian atmosphere, and therefore you don't have that heating by the absorption of solar radiation in that intermediate zone that would give that big bump in temperature. So no ozone layer, no stratosphere. We have a stratosphere in the Earth's atmosphere because the ozone layer is absorbing solar radiation. Okay, well, let's look at the standard atmosphere in tabular form. This is basically taken from Appendix E2 in the book. So it's just a numerical representation corresponding to the graph that we already looked at. And this is handy if you need to solve a problem that involves knowing what the pressure or the temperature is likely to be at a specific height in the atmosphere. And again, you might have to interpolate between different levels, but this provides a tabular representation of the temperature and pressure changes for given heights. Sea level, as always, is defined to be 0 in height and is associated with a defined pressure of 1013.25 hectopascals. Again, that's a standard value. That's not necessarily the value on any particular day. And it has a temperature of 15 degrees Celsius. And these two factors, the pressure and the temperature, combine to give you a density of about 1.25 kilograms per meter cubed. Denver is not at sea level. Denver is known as the mile-high city, and so it's about 1.6 kilometers above sea level. So if you look in the table and find a couple of levels which bracket 1.6 kilometers, it turns out that the pressure in Denver is going to be around somewhere between 825 and 850 hectopascals, and the density will be correspondingly less. It's about 1 kilogram per meter cubed instead of 1.25 kilograms per meter cubed. And the temperature in the standard case would be between 4 and 5.5 degrees Celsius. Of course, we know that Denver's actual temperature varies quite a bit more than that from not only season to season, but even day to day. And again, we can work our way up to jet airliners, which are going to be up around 11 kilometers or so, and have pressures ranging from 175 to 250 hectopascals. The temperature in the standard atmosphere would be a pretty chilly minus 56.5 degrees Celsius. And the density of the air at that point is getting down to about 0.3 to 0.4 kilograms per meter cubed. And there we have the SR-71 spy plane way up there, where the air density is only about 2.5% of sea level. Just to reiterate, sea level pressure can and does vary widely from the standard value, but the standard value is a good reference if you have to pick something reasonable to use for some kind of a simple calculation. And the same is also true for the surface pressure. That also varies at sea level, but it also varies quite strongly as you go from one altitude to another, which is also important. Okay, so we've talked about the standard atmosphere. Now let's look at some variations. So let's look at typical seasonal variations in profiles of temperature in the middle latitudes. Keeping in mind that every profile is different from day to day and from season to season, but there are certain features you expect to see change as we go from winter to summer and back. This is again Dodge City, Kansas. It's just a random station I picked because it was convenient. And we're looking at a summer sounding at 7 p.m. That is 00Z on July 4th in the year 2004. That's the solid black line. And the surface temperature is a fairly warm 32 degrees Celsius on that day, so it'd be around 90 degrees Fahrenheit. And we also have a sounding from January 27th in the same year, and this is a morning sounding, so 12Z or about 7 a.m. Central Daylight Time, with a morning temperature of about minus 10 degrees Celsius. So that's 10 degrees Celsius below freezing, or 18 degrees below freezing on the Fahrenheit scale, and 18 degrees below 32 is plus 14 Fahrenheit. So minus 10 Celsius corresponds to 14 plus degrees Fahrenheit. So this is the expected result. You'd expect to see warm temperatures at the surface in the summertime and significantly colder temperatures during the wintertime, most of the time. Okay, so looking at the same soundings, let's look higher above the surface. The summertime sounding, the one where the surface temperature is about 32, 33 degrees Celsius, is associated with a tropopause, in this case, at about 15.8 kilometers. And if you look at the temperature scale, you're going to see that it's pretty cold. It looks like it's about minus 65 degrees Celsius in this case. The tropopause is not actually at the exact point where it reaches the coldest temperature for reasons that I'm not going to go into, but it has to do with the rate of change of temperature with height that is used to formally define where the tropopause is. But you can see that it gets even a little bit colder still, a little bit above that point, but it's all essentially the same idea that the tropopause is in a range of about 100 hectopascals in this case, maybe a little bit more, and about 16 kilometers above the surface. And it's quite cold, minus 65 to minus 70 degrees or so Celsius. The tropopause in the wintertime sounding is lower. Instead of being at 16 kilometers, it's at 10 kilometers. And instead of being around minus 65 to minus 70 degrees or so Celsius, it's around minus 55 degrees Celsius. So it's warmer and lower. This is a fairly common thing we're going to see, is that when you look at the seasonal changes of the temperature profile in the middle latitudes, the surface temperatures, as we expect, and the lower tropospheric temperatures, as we expect, are going to be warmest during the summer and coldest in the winter. But the tropopause is typically higher and therefore colder in the summer, and is lower and therefore warmer in the winter. So it's kind of counterintuitive, but you can think that when it's warmer at the surface, the tropopause is likely to be colder than when it's colder at the surface because of the changing height of the tropopause that goes with the seasons. Generally lower tropopause in the wintertime, higher in the summer, and because it's higher in the summer, it's also colder. The same kind of thing can be observed if we compare a typical tropical sounding with a typical Arctic winter sounding. For the tropical sounding, we have a sounding from Borneo, which is an island which sits right on the equator in the far western Pacific. And the sounding in this case shows a near surface temperature of about 26 or 27 degrees Celsius. For the wintertime polar sounding, we have one from Resolute, which is a station in the far northern territory of Canada. And this is a January 24th sounding, so dead of winter, there's no sun. The surface temperature is minus 40 degrees Celsius. So very different in terms of the surface temperature. It's quite a bit colder at the surface, as you'd expect in the polar winter than it is in the tropics, right on the equator, right near the equator. The tropopause, in the case of the tropical sounding, is way up at nearly 18 kilometers. And the temperature at the tropopause is a bitterly cold minus 90 degrees Celsius. That's a very cold tropopause, and it comes from being so high so that temperature decrease with height gets you very far in the direction of cold temperatures before it finally stops decreasing. On the other hand, the polar wintertime sounding has a tropopause which is at only around half the height, 8.5 kilometers, and the temperature is quite a bit warmer. It's not minus 90, it's about minus 60, or not quite minus 60. So what we're seeing here is a warmer, lower tropopause for the cold Arctic winter profile, and a high cold tropopause for the warmer tropical profile. The takeaway here is that you see the same kind of behavior in the tropopause height and temperature and its relationship to surface temperature as you do for seasonal variability in middle latitudes. Surface and lower tropospheric temperatures are typically warmest in the tropics, as you'd expect, and coldest in the high latitudes, especially in the wintertime. But the tropopause is typically much higher and colder in the tropics than it is at higher latitudes. And so you expect to see a higher, colder tropopause when it's warm near the surface, and a lower, warmer tropopause when it's cold at the surface, just as you do for this winter season difference in profiles in the middle latitudes. So again, just to summarize with some rules of thumb, the tropopause is often highest and coldest when near surface temperatures are warmest. This is true in the tropics, and it's true in the mid-latitude summer. The tropopause is often lowest and warmest when near surface temperatures are coldest, and this would be true in the polar regions or the mid-latitude winter. And like most rules of thumb, they're not always true, but they're usually true, or true often enough that you can usually count on them. To summarize, in this module we covered the following topics: common temperature scales used in meteorology, starting with the primary scales that we use in meteorology, which are the Celsius and Kelvin scales, and then secondarily Fahrenheit, which is used for primarily the general public in the United States. We talked about the typical vertical temperature structure of the atmosphere, starting with the International Standard Atmosphere, which is just an idealization that is used to give a rough model for what things typically look like. And we followed that with a brief discussion of seasonal variations and latitudinal variations in the temperature profile.